All right, so this is the first video that I'm publishing for semester two. So just want to make a quick comment about it. This video is going to guide you in filling out this note sheet for variables and solving. You got a bunch of stuff to fill out here, some definitions, some examples. I'm going to do all of that, but I'm going to do it in the format that I kind of matched during instruction here using this slideshow. So work along with this, pause your screen as you go so you can try it yourself, unpause it to check your answers, and here we go. So we're talking about variables and solving equations today. So I want to define a couple of things first. First off, a variable. So that's just going to be a symbol or a value we do not know yet, usually a letter. The most common one is x. Then an equation is going to be something that states that two things are equal. So once you get these definitions down, let's move on and kind of talk about how they're going to be used today. When we are asked to solve an equation, which you've been asked to do this a billion times already now in your math career, we're going to find the value of the variable that makes the equation true. We do this by isolating the variable using inverse operations. And when we do these, we want to make sure we kind of follow the reverse order that we normally do. Usually we see PEMDAS, P-E-M-D-A-S. We're going to work in that reverse order, so S-A-D-M-E-P. Let's talk about this real quick. So if we have this equation, m plus 4 equals negative 12, if we were to try to solve this and just do guess and check and say, hey, does m equal 5, question mark? We'd plug in 5, we'd say 5 plus 4, does that equal negative 12? And it doesn't, so that wouldn't be true. M does not equal 5. However, if we wound up at an answer and say, let's say M equals negative 16, okay, if I plugged in negative 16 and I added 4 to it, that would give me negative 12. So in that case, we would have an answer of M equals negative 16. That's what we're doing when we're solving. However, we want to actually go through this in a more systematic process. So one thing I like to do is kind of think of, all right, I have this boundary in my equal sign, and I'm going to move things away from my m in order to get the m all by itself. Since the 4 is being added to the m, we use our inverse operation to get rid of it. Since that happens on the left, it's also got to happen on the right. So we have positive 4 minus 4 gives me 0, so I just have m left over on the left. Negative 12 minus 4 gives me negative 16, so I just come up with m equals negative 16 as my answer. We can use that same principle in example 2. If I kind of divide my equation into two sides, the left and the right, and then try to strip things away from my variable v, I'll add 15 to both sides because we're using the opposite operation there. And then so we'll get v left over on the left and negative 27 plus 15. Let's use our calculators there if we need it. That should give us negative 12 on the right. And finally, let's throw it a little bit different here. If I have my equation divided into two sides, this time I have 8 multiplying with x. When we have this smushed together here, what that's doing is it's multiplying with my variable x. So I want to divide from both sides in order to get my answer. And if I do that, let me grab my calculator. We get negative 104 divided by 8. That gives us negative 13. So negative 13 on the left equals, and that 8 and 8 just cross each other out, and we get x as our answer for number 3. So normally we're going to have to follow multiple steps in order to work through our equation. So let's remember that kind of reverse order of operations as well. SADMEP instead of PEMDAS. Because we want to go this way in our order of operations to strip things away. If we look at this negative 9x plus 1 equals negative 80, we have two things happening. We're adding 1 to it, and we're multiplying by negative 9. We want to start with this add subtraction first because they come in to our equation first in that reverse order of operations. So we subtract 1 from both sides. we'll get negative 9x equals negative 81. And then we can divide negative 9 from both sides to come up with our final answer. We get x equals, this would be a positive 9 in this case. To get 9, a positive times a negative would give us a negative number. All right, let's try it with example 5. Again, splitting our equation down the middle. Up to you whether or not you want to show that line or not. We're going to start with that subtraction before we do handle that multiplication. So we subtract 2 from both sides because it's being added at the moment. We get 5x. The 2 minus 2 cancels out, equals negative 10. And we get 5 times x equals negative 10, so we need to divide by 5 on both sides. And we'll get x equals negative 2. All right, example 6. A little bit different because instead of multiplication, we have a division going on here with this x divided by 4. We still want to handle the addition subtraction first, so I'm going to add 6 to both sides first, cancel that out on the left, cancel it out on the right. Negative 6 plus 6 is 0, so I'm just left with x over 4 on the left. Negative 5 plus 6 is positive 1, so I'm just left with 1 on the right. And then so to get rid of division or this fraction, we're going to multiply on both sides. So I take my 4 times x divided by 4, 1 times 4 on the right. These 4's cross each other out, and I'm just left with x equals 4 on the right side. And with all of these, if we plugged these back into our equation, we'd find that we would get the answer we're looking for. Let's take it with example 5. If we take 5 times negative 2 instead of x plus 2, we would get negative 10 plus 2, and that equals negative 8, which is exactly what we want here there. So that is true. We can count that as correct. As we get more complicated, we may need to simplify or combine like terms before we finish out our problem. So I want to show you 7 and 8 as nice exposure problems to hit this higher type of questioning. In example 7, we see that we have 2w plus 3w equals 30. So before I can divide anything away, I actually need to combine these terms first. Get 2 of something plus 3 of something, we end up with 5 of that thing. And then I'm left over with an equation that I can solve where I can divide out the 5 from both sides and get left over with w equals 6. This can also show up where we have a split in our equation and the terms are on opposite sides. Notice how I have a 5v on the left, I have a 3v on the right. So a good trick is to think of like, all right, I'm going to get all of my variables over on the left side. I'm going to get all of my constants over on the right side. And then I can start working at dividing things out. So I'm going to move my 3v over to the left by subtracting it from the left. I have a positive 3v minus 3v. And I got to do that on both sides of my equation. So 5v minus 3v equals 2v. The 1 just comes straight down, equals 3v minus 3v is 0. That 5 just comes straight down. And then we have a problem similar to before where we can use our multiple steps. We can move this constant plus 1 over by subtracting. We are left with 2v equals 4. And then we can divide out the 2 from both sides since it's being multiplied right now, and we get v equals 2. Now, the last thing I want to talk about is I want us to start getting exposure to doing this graphically because this is something that will be a surefire way to get our answers right on our end of course assessment. So we can use the software called Desmos to graph everything and actually solve this equation, but we need to treat each side of the equation as separate functions. Once we do that, we can locate the intersections, and then we just pull the x values of these intersections in order to come up with our solution. So let's try that with example 7 real quick. If I go back to example 7 and let me clear our selections here. If I go back to example 7 and do what I'm talking about here, I'm going to show this 2w plus 3w. I'm going to plug it in as y equals 2x plus 3x. And I'm going to plug in this 30 as y equals 30. And so we go to Desmos, and we want to use the NC test version of Desmos to make sure we are limited to the right answers. And we're going to plug in those two equations, y equals, so my top line, y equals 2x plus 3x, and my bottom line, y equals 30. And notice if I zoom out and find both of my graphs here, I didn't have to do any math. I literally just had to type this stuff in, and I got two different lines, my red line and my blue line. If I locate the intersection of that line, which is, I'll zoom in a little bit so we can see it better. I have an x value of 6 here. I have a y value of 30. And so that x value, that input, is going to be 6. So let's say green equals 6, x equals 6 from graph. But in this case, since we're using w, it's really w equals 6 in our equation. And that's exactly what we got when we solved this through manually. Now, if we try that again with our example 8, now we have our red equation. We'll say y equals 5x plus 1. And let's call it our blue equation, y equals 3x plus 5. Okay, we'll go into Desmos. We'll graph these two things, y equals 5x plus 1. And I believe it was 3x plus 5. Let me double check that. Yep, so we get another two graphs. We can zoom in here to try to see where that intersection is. That gray dot locates it, and it looks like we have an x value of 2, a y value of 11. So our solution should be x equals 2 here from our graph. And so that means that v equals 2 in this equation. So if you're making up this work, finish out the notes, make sure that Mr. Ratisha sees them, and move on to the practice problems which are posted on Canvas.